let's keep talking about limits. You guys will find that what I'm doing in this section is continuing to kind of give you like smattering of ideas, all of them you need to know. But we kind of come back to something which is actually what's gonna happen now. So here's our next example. It kind of fits back into, here I'm giving you an actual function as opposed to like the little make-believe functions that we left with. And as you are building a little more knowledge, how would you approach this one? We'll talk about it together, but you realize that you have a couple methods to be able to kind of approach one of these. One of the methods is like a substitution. I see some of you punching some buttons. Let me encourage you to consider the substitution method because honestly, it's kind of your first line of defense. It's supposed to be a little more fundamental. Plugging in 0 as a substitution, well, what does it tell us? Now, don't be too quick to kind of say, you got a 0 in the denominator, because I hope you realize from that slide that I had up here that a 0 in the denominator, yes, but what about the numerator? Okay, you kind of have to be thinking about both. So the tangent of 0, it does go back to the unit circle, although right now we'll just say that you can get 0 for the tangent, and of course now you have 0 to 0. This is an important spot to be at. I don't want you thinking that that was a waste of time, but I do want you to realize that it doesn't tell us anything. The reason it's an important spot to be at is because what if it did tell us something? We'd be done. Okay, it just tells us that this is an indeterminate. An indeterminate, indeterminate. It's kind of weird, you can write something on the board and it just looks different, but we gotta do something else. Okay, now what's that something else? Yeah, you could graph it. Okay, you could graph it. Now if you were graphing it, let's go down that road and see what happens. By the way, I don't expect you to know what this graph looks like. Many graphs we have the calculator to help us with, and it's a realistic, it's a reasonable tool. You're allowed to use it. Now I hit zoom trig, and I realized because I used this calculator for different things that I was in degree mode. So radians and zoom trig gives you that. It's fancy, and you probably aren't surprised that it's got some asymptotes. All that stuff is good and well, but all that really matters is what's happening as we approach 0. So as you guys do more of these, you kind of have to force yourself just to look. You have to force yourself to look at the C value, at the X value. Now, you can just look. You can tinker around with the trace button. You probably have to do something to get some Y values. I'm kind of tinkering around with the trace button and I see my Y value at 1.0, getting closer to exactly 1.0, and then when I get right on it, it vanishes. When I look on the other side, I can see the same thing. Again, that it's getting really close to 1. It's getting really close to 1. In fact, visually, it wants to get to 1. Visually, the intended height is y equals 1. Again, the intended height is y equals 1. So we can kind of modify our answer. We can actually give an answer. Again, the intended y value visually looks to be 1. Now, even as I say that, I feel like there's a little bit of uncertainty, a little bit of but how do you know? How do you know for sure? What if it really isn't 1? Okay, well, it is 1, but there's a way to know for sure. And that way is to use what I'm going to call kind of a third method. It's kind of like algebra, but it's a little more analytical. So we had like a substitution method. Nothing wrong with it. Sometimes that's all you need. We had a graphing method. I don't want you to think that there's something wrong with it, but it kind of feels like there should be something more certain. And that brings up what's known as an analytical method. An analytical method kind of feels like algebra on steroids, a little bit more mathematical. So we kind of think a little more about algebra. That word algebra, it's a pretty big umbrella, so in this case it's actually some trigonometry and algebra. But to kind of help us get started, we're gonna do something to tangent. We're gonna change it. In a sense though, we're just gonna change its appearance. It's still tangent, but we're gonna give it a little facelift. Okay? In other words, we're gonna say that tangent from last year is sine over cosine. Sine over cosine. Now it's kind of one of those things that, you know, maybe I have to tell you the first time. Of course, after I tell you, you should say, okay, that's just a property, it's actually an identity from last year. Now, if you're saying, how do I know to do that? Sometimes we have to experience a problem, so next time you know that you can do that. So let's keep experiencing this. Because what I also want to do is I want to make sure I don't mess up like what we really have here. And in other words, what we really have is 1 over x, 1 over x. Now again, as a math student sitting in calculus right now, I hope that you look at both those statements and say, okay, just knowing that is still true, like it's still equal. I just kind of change the look of it a little bit. Okay, but there's a reason I'm changing the look, and this starts to get more to the calculus. There's a reason. Sine over cosine times 1 over x. There's no reason I can't rearrange that algebraically to be sine over x times 1 over cosine. Again, algebraically, there's no reason I can't kind of rearrange the denominator because it's still the same idea. I'm dividing by x, and I'm also dividing by cosine. And by the way, sine is still in the numerator, so I'm multiplying by sine. Now, I have to admit I'm being a little sloppy here, and I shouldn't be, but I'll forgive you. And I ask for the same thing back, that if you don't write limit every time, I'm not gonna take off that, but we're still doing the limit of this. And I do wanna write that because I'm just wondering if that looks like something. I'm wondering if the sine of x over x looks like something from yesterday, like that you know. Now it's already to page back in your notes, it's probably a good experience to page back. Say, what am I paging back to? Well, does the sine of x over x, does it look like something that you know? And now here's kind of the way it goes. If you knew that answer yesterday, or maybe yesterday we found it, it's still the same answer today. What I'm suggesting is that you can do this limit. You know it from prior knowledge. The intended height of sine of x over x. Okay, just make sure that everybody's looking at the right thing. I'm referring to this right here. The limit of the sine of x over x as x approaches 0. It was 1 yesterday, it's still 1 today. And so I can take this, and I always struggle with how to show the work here because I'm not really doing any work. I'm just saying that it equals 1 from yesterday. And maybe more from just like a sort of a given fact or a proven fact that the sine of x over x intends to approach the number 1. What about this? You don't know it from yesterday, okay? But you can do it today. What do find the limit of 1 over cosine. Kind of don't be like worried or scared about doing that, because you'll find out that 1 over the cosine of 0 is actually just equal to 1. Make sure you put in your calculator, it's equal to 1. Yeah, that's because the cosine of 0 is equal to 1. Look what happened here in this problem. I think we can see that the answer is going to be 1 times 1, which is 1. But look what happened in this problem. We took something that was not known, that is the tangent of x over x. Like, I didn't know anything about that analytically, but I turned it into 2 things that I do know. I turned it into 2 things I do know, and now it doesn't have to be the same answer. Okay, but it's a little bit more of an analytical method, like a proof almost. And that becomes like a third strategy for limits: substitution, wrapping, analytically, or analytical method. Thoughts? Are you sure? You guys okay with what happened in both these boxes? Okay, it's kind of crossing your mind like, well, how am I supposed to know if I'm supposed to do this? Sometimes it's getting the experience. In other words, we're going over it, and you're going to try the assignment, and then you're going to check your answers in the solution manual, and you start to gain that experience. So you'll see a problem where you'll be able to do something like this with sine and cosine. Okay? That's the big one, though. You'll realize throughout this chapter that sine of x over x is known. It's known to be 1. Okay? So of course that'll be true tomorrow and as we go forward. Let's do one more kind of just example, and then I have a different type of problem to work out with you. Okay, so obviously it's another limit where we actually have a function, we have an equation. Part of the reason I'm doing this with you is because I want you to say substitute. Okay, it should be the first thing that you think about. Now, yes, you should notice that the denominator comes out to be 0. But you have to now realize that the numerator is equally important to this conclusion. So when I plug in -2, it's like you get -8 plus 1, otherwise known as -7. You don't need a calculator. You don't need to graph it. You just need to kind of get to know your limits. And if you end up with a number over 0, now that means a non-zero number over 0. So if you end up with this middle category, it's a vertical asymptote. Vertical asymptotes don't have a limit, okay, because I'm going nowhere. At least I'm not going to an intended height. So once again, the limit does not exist. The limit does not exist. And kind of purposely doing that problem that you realize that there's nothing else that we need to do. We don't need to look at the calculator to start to be confident with that. Okay. Piecewise functions. They're an interesting group because they kind of show up at different times this year, and they say, let me be part of your calculus. Let's do a calculus to a piecewise function. Today, what I mean is let's do a limit of a piecewise function. And our goal, as really as our goal for this whole chapter, is to be able to realize that, well, let me call this f of x. Our goal is to understand that the definition of a limit is not going to change. It's It's not gonna change just because we have what appears to be a different type of function. It's always going to be an intended height. Let's see how the idea of an intended height gets worked out with the piecewise function. So we got x minus 1 from x less than 3, and then we got 0, x equal to negative 3, x plus 4, x greater than negative 3. Okay? And make sure that you notice this. We're trying to find a limit as x approaches negative 3. Okay. Piecewise functions typically have like a graphing kind of expectation. Like we almost always graph them. And that is definitely part of, and a big part of getting this limit correct. I'm going to go with kind of a no calculator approach because we should be able to graph these pieces pretty comfortably without a calculator. This piece right here, negative x minus 1, that's a straight line. It has a y-intercept of negative 1. It's got a negative slope. Now, I always like to kind of just visualize the line, because you know as well as I do that those lines can end up tilted the wrong way, even if you're well intended. So it's a negative slope, it's tilted that way. Now plugging in negative 3, finding the end point, or if you will, the beginning point, whatever you want to call it, that's also a good idea. I plug in negative 3, and I end up getting a y value of 2. Now you say, yeah, but it's not equal to negative 3. Okay, negative 3 comma 2 is just going to be the place where this piece begins, okay? But we will carefully denote that with an open endpoint, with an open circle. Okay, notice that I'm paying attention to y values. As you begin to understand limits more, you realize that y values are a big part of our analysis. So I want to pay attention to the point negative 3, 2. I'm going to label it, I'm going to mark it. How about this piece? It's kind of weird because it's actually not a line. It's not a line. It's a point. X equals negative 3, y equals 0. X equals negative 3, y equals 0. It's a point on our piecewise function. Okay, but we took care of that piece. The last piece to do is another line. It's a line that has a y-intercept of 4. It's got a slope of 1. And even as I teach the algebra kids, it's just a good idea to visualize that line before you get too much into the final answer. So there you go, it's tilted the right way. Plugging in negative 3, a good idea because it gives you where this line is going to start or stop, however you want to call it. It gives you a y value. Plug in negative 3, you get 1. Make sure your graph looks good. We haven't really talked anything about limits yet, but we've done all the dirty work. Okay? Because when it's time to talk about limits, it's time to think about intended heights as you approach negative 3. Intended height as you approach negative 3. Now, I could approach negative 3 over on this piece. And since I'm approaching negative 3, then I should be walking down this line. Kind of going down. What intended height am I approaching here? Well, we already found it to be 2. We already found it to be 2. Make that look a little better. How about this piece right here? If I'm gonna approach -3, then I should also be walking down. And I get to, I get to an intended height of 1. Now, how's that going for you? As you approach -3, as you approach, now notice that we're always approaching from both sides. So as I approach, how's that going for you with intended heights? Now there might be a little bit of uncertainty here. You might be like, is the answer 2? Is the answer 1? Okay. The answer is, do I approach an intended height? And implied by that would be 1 intended height. 1 intended height. So the simple answer is no, okay, because they're different. They're different intended heights. Now, go with me with this for a little bit here. The limit does not exist because the heights are not equal. Again, the limit does not exist because the heights are not equal. But if you're feeling a little bit like, yeah, but, Mr. Naylor, but something exists. You know, like it, 2, it looks like I was intending to get to 2. Okay, well that's something that you're kind of sensing there, or at least I want you to be sensing, is our next idea. Okay, it's called the left-hand limit. Now, the left-hand limit, let me see where I want to put this. The left-hand limit is the limit as I come in from the left. As I come in from the left, I end up with a limit. I end up with an intended height. And I denote that with a little negative sign. Now, watch carefully, okay, because this little negative sign ends up here as like a superscript. So I've got the limit as x approaches -3, but we've got this little negative sign. It's not just a straight mark. And that means the left-hand limit. And again, that would be the limit as I come in from the left. For this problem, it would be 2. Well, you also have something called the right-hand limit. And the right-hand limit, sometimes the word sounds kind of so just generic that you might think I'm making this up, and I'm not making it up. It's actually good calculus. It's called the right-hand limit. It's the limit as you come in from the right. Now, the limit as I come in from the right was this limit of 1. It was this intended height of 1. But we denote that by saying the limit as x approaches -3 with a little plus sign. A little plus sign. It's a superscript. You'll see it when it's printed in the textbook or on a paper, but it's not a straight mark. And that limit is equal to 1. Because that was the intended height on the right side. Now I want you to notice something here. I think it'll be the last thing that we do today. But it was kind of what we already said, just makes it a little more official. Okay, and that simply is that these 2 left and right hand limits are not the same. They're not the same. And when they're not the same, then the limit does not exist. Now, when I say the limit does not exist in this context, we call that like the overall limit, or sometimes the general limit. The general limit. And just to be clear, the general limit, it didn't exist from the beginning. But that's because the left and right hand limits, although they existed, were different. Okay, now we'll kind of take this and we'll continue to put it together. There's one more teaching day with this lesson. I like to take it nice and slow.
So do you not do anything with like the one that's at 0?
Ah, good. I may have forgotten that he didn't ask, but what's up with this point right here? Okay, actually, the answer to your question is yes, we don't do anything with it because it's not an intended height. It's just a place, it's just one point. To maybe say another way, I don't approach that point. I approach on the graphs. I approach on the graphs, but there's no way to approach those. So yeah, you kind of don't do anything with it yet. It'll be something that we'll mix in a little later. Okay, now, I did give you the assignment paper. If you want to start looking at it, you know, because